Hello everybody, this part of the video is going to be learning how to draw Lewis structures when they have double or triple bonds. So I'm going to start with an example that has a single bond, and then I'm going to show you how to do a double and triple bond. The way that I teach this I think is nice because there's a set of steps that you're going to follow. A lot of people just teach this by saying put the dots all over until it works, and that's basically guessing and checking to a degree that makes it pretty overwhelming because you have no pattern to follow. You have no set of steps to go off of. So sometimes this may take a little bit longer than guessing and checking, but it's a much safer way to go about doing these problems, which I think is good because you want to try to get them right as often as possible. Okay, so let's start. We're going to start with H2. Remember steps where we had to count first, count our valence electrons. So I have two hydrogens. They each come with one valence electron. So that's a total of 2, which is the same as one pair. Then I'm going to place my elements. This time it's easy. Hydrogen has to go on the outside, but that's all I have, so they both go on the outside. Then I give them a single bond. Then I'm going to give them a full shell. But if you look, hydrogen is already full with 2. Remember, it's so tiny it only wants to have 2 valence electrons. So each hydrogen now feels like it has 2, so it's finished. If I want to replace it with a line, it would look like that. That's an example of our single bond. Now let's do O2. First I need to count. I have 2 oxygens. They each come with 6 valence electrons, 12 electrons, or 6 pairs. So for the purposes of our notes, I'm going to kind of redraw it after each step so that you can kind of follow your notes afterwards. So first we place our atoms. This time it's pretty simple. There's not a lot of choice. I bond with a single bond because that's the simplest. Let's pretend it's the simplest. I'm going to give everything a full shell of 8. Let's pretend these oxygens could have everything they wanted. Let's see if my drawing worked. 1, 2, 3, 4, 5, 6, uh-oh. There are 7 pairs. If I draw the simplest version possible, we find out we can't do it. It would require too many electrons. We don't have 14 electrons to use. We only get to use 12. So the simplest version is not going to work. So let me redraw this down here so that we can kind of change it a bit. Now remember, this is just a drawing. This is just a picture. I'm allowed to change a picture, right? So what I'm going to do is I'm going to find 2 atoms that are next to each other, which for this case is super easy. That's all we have. I'm going to take a pair away from each. And then what I'm going to do is I'm going to put 1 pair back. Because right now if I took 2 pairs away, we wouldn't have enough electrons, would we? I'm trying to get my pair count down by 1. So I'm trying to go from 7 to 6. But I took 2 pairs away. So let's put 1 pair back into our picture, but we have to think about where to put it. So I take a pair away from each. So then right now, it's going to look like this. And if you notice right now, neither of these oxygens has a full shell. They're not happy. So what I can do is if I'm going to put 1 pair back, I'm going to put it back between them and that makes a double bond. When I make that double bond, they're now sharing. So if I look, they each feel like they have 8 electrons. That oxygen feels like it has 1, 2, 3, 4, 5, 6, 7, 8. This oxygen feels like it has 1, 2, 3, 4, 5, 6, 7, 8. When I count them up, I now have 1, 2, 3, 4, 5, 6 pairs, which is what I wanted, right? So that's good. So if I want to redraw this with lines, and then we put our lone pairs back, and that is a double bond. So what I did was I counted, I placed my atoms, I bonded with a single bond, I gave everything a full shell, and then I recounted and found out that didn't work. So then to fix it, I take one pair away from each picture, or from each atom in the picture. I put a bond between the atoms, and then I recount again, and it was fixed. Oops. Let's do another one. Let's do N2 this time. There's 2 nitrogens. They each come with 5 valence electrons. So now I place my atoms. I give them a single bond. It's just a picture, so let's see what happens if I make it as simple as possible. Let's see what happens if I just put lone pairs everywhere. Okay, let's count. 1, 2, 3, 4, 5, 6, 7 pairs. I was only allowed 5 pairs, so this is not good and really not good. Okay, so what we're going to do, I'm redrawing it just for the purposes of our notes. I wouldn't make you redraw it every time on your homework. Okay, so what I'm going to do, I'm going to take a pair away from each atom. It doesn't matter, you could have taken the ones on the top, you could have taken the ones on the end, as long as they're on atoms that are next to each other, it doesn't matter. So I took a pair away from each, and I put a pair in the middle. Now if I count, we have 1, 2, 3, 4, 5, 6 pairs. Okay, well, that's still bad. This one was like really bad, and now it's just a little bit bad. So we're just going to do it again. Okay, so for the purposes of our notes, I'm going to redraw it. I'm going to take a pair away from each, and I'm going to put a pair on the inside. Now I have 1, 2, 3, 4, 5 pairs, which is what I wanted. So now let's redraw this. And that is a triple bond. Some people will probably ask, could I have gotten points if these lone pairs were on the top of the nitrogens or on the bottom? Or what if I had one on the end and one on the top? That's totally fine. In real life, they have a 3D structure that we'll learn about. And when we start learning about the 3D structure, you'll start seeing why we tend to put them in certain places. But I wouldn't stress about it right now. Okay? So up at the top, I'm just going to make like a little key. Now that you've seen a single, double, triple, if we have 2 dots, that's a single bond, right? And that's 2 electrons being shared. If we have 4 dots, that's a double bond. That's 4 electrons being shared. And then if you have 6 dots, that's a triple bond. And that would be 6 electrons being shared. So now let's do a couple examples where we have more than just 2 atoms, because that's when it starts getting a little bit more complicated about where you're going to put these double and triple bonds. So let's do CO2. I'm going to count my valence electrons. I have 1 carbon that comes with 4. I have 2 oxygens that come with 6. I get a total of 16, which is 8 pairs. Now, to place my atoms, remember carbon is less electronegative, so it's going to go in the center. I'm going to try to put the rest of the atoms going around the box. 1 oxygen on one side, 1 oxygen on the other. I'm not going to put it down here because I want to spread them as far away from each other as possible, right? They don't want to be crowded. So that's why I'm putting 1 on each side. Now I'm going to single bond so that nothing's floating around by itself. I'm going to give everything a full shell, and I'm going to cross my fingers that it works. Let's count. I'm only allowed 8 pairs, but I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 pairs. One of the reasons why I like this method is if you look at this, 10 minus 8, 2, I have to add 2 bonds to this. It will tell you how many bonds you have to add, okay? So I know I'm going to have to add 2 bonds, so I can start to think about, okay, where am I going to put those 2 bonds? Where might be most symmetrical, okay? So let's do the first one. I'm going to take a pair away from each atom next to each other and put a pair in the middle. I cannot take a pair from each oxygen because they're not next to each other. We can't make any kind of arching bond. We can't skip over an atom. So I could have done these 2 or these 2. It doesn't matter which. I'm just moving left to right. Okay, so now let's recount. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9 pairs now, which is better, but it's still not great. I have 1 left. So let me redraw this. Because at this point we have a choice to make. This is where people start, always asking, what about this? Could I have done that? Would this answer be okay? All right, so option number 1 is we could make a triple bond over here. If I make that triple bond, my molecule would look like this. Oxygen feels like it has 8, carbon feels like it has 8, the oxygen over here feels like it has 8. There's technically nothing wrong with this structure. The other option is to make a second double bond instead. So what I could have done instead is that. So you have to stop and think, well, which of these is better? They're both what we call valid They both meet all the criteria, but there is one that's better. This one is better because this one is symmetrical. So what you have to always make sure you're doing, which is hard, is you have to pick the best answer. Because that's showing me that you understand that in real life, the best answer is going to be the one that's symmetrical. When things are symmetrical, you know, all the electrons are spread out as evenly as possible. You get the lowest amount of repulsions, right? It's the one that's most likely going to exist in the highest quantity in real life. These may both exist. They're what's called resonance structures, where you have two valid structures. The atoms are in the same places. You've just moved the electrons around, right? But this resonance structure is going to be a little bit better of a choice. It's going to exist probably in a higher quantity. Okay, let's do another one. I have one hydrogen that comes with one valence electron. I have one carbon that comes with 4. I have one nitrogen that comes with 5. So altogether, I get to have 10 in my picture, or 5 pairs. Now we know hydrogen has to go on the outside. Now, if you look, carbon is less electronegative, so I'm going to put that here. And then I'm going to put nitrogen on the outside. I'm going to single bond everything so nothing's floating around. And I'm going to give everything a full shell. Remember, hydrogen is already full with 2, so leave it alone. I don't ever want to see more than 2 electrons with a hydrogen. That would be crazy, okay? Leave it alone and fill the rest of the molecule up. So now let's count. 1, 2, 3, 4, 5, 6, 7 pairs. I was only allowed 5, so I know I have to add 2 more bonds here, don't I? And when I look, hydrogen's full, so I cannot add a bond over here. This is finished. So both of my bonds are going to end up in here. So instead of a single or a double, I know I'm going to end up with a triple, which makes sense because nitrogen loves triple bonds. It doesn't have to have them, but I'm not surprised when I see that. So let's fix this. Take a pair away from each and put a pair in the inside. And then count. Now we have 6 pairs. Better, but not great. For the purposes of our notes, I'm going to redraw it. Take a pair away from each, put another pair in the middle. 1, 2, 3, 4, 5 pairs. That's good. So with dots, it would look like this. With lines, it would look like this. I have a single bond, I have a triple bond, and I have a lone pair. All right, sometimes you have what are called chunked formulas, where the way they write the formula is trying to give you a clue about something. So let's look at some examples. This formula probably looks fine to you. This one probably looks weird, because why did I split the hydrogens up? In both of these, I have a carbon, I have 2 hydrogens, and I have an oxygen. So they should, in theory, be the same, right? Except they're not. They're super different. They're going to have different shapes. They're going to have different properties, okay? So let's do step 1 for both. We have 1 carbon that comes with 4, 2 hydrogens that each come with 1, 1 oxygen that comes with 6, 12 electrons, 6 pairs. Over here, I'm just going to count in exactly the order we see so that I don't miss anything. I have 1 carbon that comes with 4, then I have 1 hydrogen that comes with 1, then I have 1 oxygen that comes with 6, and then I have 1 more hydrogen that comes with 1, which is also 12 electrons and 6 pairs. Okay, so they even have the same number of electrons. But let's look at how they've chunked the formula. Hydrogens are often a clue, so you want to kind of break it up where the hydrogens are. So I'm going to have a CH2 chunk and an oxygen chunk over here. And on this side, I'm going to have a CH chunk and an OH chunk. And that's going to help me figure out where to place my atoms. So let's just do this one first. I'm going to have carbon in the middle, and I'm going to have hydrogen on the outside. Attach those with single bonds so nothing's floating around. Now I'm going to have to attach this oxygen. I can't attach the oxygen to hydrogen because hydrogen's already full. So I can only attach it to that carbon. Let's place our atoms over here. I'm going to have a carbon with a hydrogen attached. It doesn't matter, you could put the hydrogen on the top or the bottom. I just am going to spread it out as far as I can so I know it's going to be on the left. So now that portion needs to connect to this part. The OH cannot attach to the hydrogen because hydrogen's full. So I'm going to have to put the oxygen here, and the last hydrogen goes on the outside as well. Single bond everything. So already you can see 2 very different structures. Let's give everything a full shell. Remember, hydrogen is full with 2. Now let's count. 1, 2, 3, 4, 5, 6, 7 pairs. Over here, 1, 2, 3, 4, 5, 6, 7 pairs. Neither of those are happy. Take a lone pair away from each. So carbon and oxygen are next to each other, so I can take a lone pair off of carbon and a lone pair off of oxygen. And then put that pair, 1 pair back in the middle. Over here, I'm going to take a pair away from carbon, a pair away from oxygen, and put a pair back in the middle. Let's just skip to drawing it with lines. So now that's one of my structures. And over here, that's another structure. 1, 2, 3, 4, 5, 6 pairs. 1, 2, 3, 4, 5, 6 pairs. So both of these structures, when you look at them, they have the same number of atoms, they have the same type of atoms, they have the same number of lone pairs, they both have 2 single bonds, they both have a double bond, they both have 2 lone pairs, but they're completely different molecules. The structure really, really matters. Okay. All right. Down here, we're going to do 2 little examples of things that you need to make sure you don't forget about. Okay. So the first is going to be lone pairs. Something about lone pairs is important to keep in mind for when we start looking at the 3D structure. So let's do water. This is the structure for water. most people would draw it like that. The problem is it is not straight. Water is actually bent. Water looks like this. These lone pairs here take up a lot of space, okay? And what ends up happening is the electron repulsion is going to push these atoms down out of the way. And what ends up happening is the structure ends up bent. It's distorted the shape, right? So we often call these Mickey Mouse ears, right? They're going to push these hydrogens down out of the way. NH3 is another example. We maybe draw it like this on our paper, but in real life, it's not like a T shape like this. In real life, we have the hydrogens ending up really bent downwards. So this nitrogen, its lone pair, pushed those hydrogens down. So it almost looks like a piano stool. I don't know if you've ever seen one of those where the three legs, it's so hard to do under the camera, but you see how it's like my fingers are kind of pointing downwards like this, and at the top there would be the lone pair. Okay. The last little thing I want to mention is polyatomic ions. Polyatomic ions are things with a charge, an ion, that are made from atoms that are covalently bonded together. Then we have each of these, polyatomic ions go join with a different ion to make an ionic bond. But inside the ion itself, it's covalently bound. So let's do Cn minus, for example. The big deal here is that we have a charge. Can't forget the charge. So often people just don't even notice the charge. So I have carbon that comes with 4 valence electrons, right? That's the carbon part. I have 1 nitrogen that comes with 5. If I were to add those up right now, you would notice that this is an odd number of electrons, which is really bad. That would be so crazy reactive. It would be what's called a free radical, and it would be, zooming around, yanking an electron off of things. Single electrons are not good, okay? We always want them in a pair. So if you find an odd number, chances are it's an ion, and you have to take into account the charge. So we have to also add in, if it's a -1, that means it gained 1 electron, okay? So right here, this extra electron is coming from the, coming from the charge. So down here, this is the charge. Now when I add that up, oops, 10 electrons, which equals 5 pairs. When I draw this, I'm going to have carbon, nitrogen, it ends up with a triple bond, ends up with some lone pairs like that. And then the problem is people stop and they don't get any points. Because right now, the way you drew this implies that if carbon and nitrogen bind naturally, with their normal number of valence electrons, this is what it would look like. But this is not what it would look like. This is of the ion. So what I have to do is I have to put square brackets, and I have to put the charge on the outside as well. That's telling people that this gained an electron that it wouldn't normally have. And that's why it's allowed to make that structure. Okay. Now, one of the things that's hard about Lewis structures is that it does take a little bit of exposure to seeing common molecules before you start getting a feel for things like where to place your atoms. You're going to get to the point where you're going to just instantly remember that N2 is a triple bond, right? You're going to know after doing it a couple of times that oxygen's a double bond. You're going to know after a couple of times that CO2 likes to make two double bonds like that. There will be ones that you see over and over again. But then you might get one that's weird, and you have to make sure that you're being very careful with following the steps, because that's going to set you up with the highest chance of getting it correct. Okay? All right, everybody. That's it for this part of the video. I hope that was helpful. Bye.